All right, this seems like forever ago, but let's pick up kind of where we left off, which was talking about confidence intervals. Right? Is that what we did? Good. It's like 2 weeks ago. When we talk about a confidence interval, again, this is all relates back to that idea that we have with a distribution of scores, and we have a theory that when you have really large numbers like populations, that events that occur in nature are naturally distributed. So shoe size, for example. There's some people out there with some really small feet. If I want to be crude, I could say some people are born without feet, which is technically true. So their shoe size would be 0, which is the end. And then you have Shaq, who today I'll say is a size 32 shoe. It's more like 25, I think, right? So we have the extremes on both ends, but for the most part, we have, we have a normally distributed, and within that population there is an average size, an average shoe size, an average hat size. But when we take a sample, because as social scientists, we have to deal with samples. We can't interview the entire world. We can't look at the 200 million or so voters that's going to vote next week and ask them all a set of questions. We have to take a sample. Well, it turns out how we collect those samples are also normally distributed. And if you remember last class, I did the little simulation where I kept hitting the button and it kept drawing a sample, and we wanted to know how close our sample mean was to the population mean. And I kept hitting and hitting and hitting, and eventually, once we hit like 100 and something, my sample mean was where we thought the population mean was. So today, again, we're going to go over confidence intervals, and we're going to make sure we understand what it is that we're talking about. And again, this is from last class. You take a normal distribution, we put the mu, which is the population mean, in the middle. And then depending upon the level that we're looking at, which is most commonly 95%, where alpha equals 0.05. Right. We're putting the confidence level in the middle, which gives us 2 tails. Okay. We're going to split that up and put it in the tails. And then we're going to look up the z-value for the tail. So this is just another way of using our equation where z equals the difference of the means divided by the standard error. Okay? We are all feeling z-scores. We know how to do it. We're just going to do it slightly backwards. Okay. So here's what I want to do today. We're a little rusty. We need to get back into shape. I've given you a homework assignment. Let's look at a couple of the questions from the homework assignment. Sort of. I mean the odd numbers. Yep. So, for question 1, it says, for each of the following situations, calculate a 95% confidence interval for the mean. Sigma is not known. Beginning with the step, calculate the degrees of freedom and identify the critical value of t. Okay, so A, our n is 15, which means we have how many degrees of freedom? Our x bar is 6. And our standard error is 1.5. Okay. all I've done with this equation is reconfigure that t-score or z-score equation, right? I know what my confidence interval is. That's going to tell me what t I need to use. Bucket on the floor. Not enough of you did this on the test. I've met with 3 or 4 of you since I handed back the midterms, and we were going over questions, and you missed questions where you didn't start with the bucket on the floor. Draw the curve first, so that way we know what we're doing. Our sample mean is 6. The question asks us to create a 95% confidence interval. Never to scale, but so that I know what I'm doing, which means how much is going to be in each tail. Okay. Why do I draw the picture? So that if I get confused, I can look at the little picture at the top of the table and go, okay, what exactly is it that I'm looking for here? Okay. So what exactly is it that I'm looking for here? Huh? What exactly is my next step? I'm trying to find a 95% confidence interval. I have a sample mean of 6. And I need to know where those lines that are my confidence intervals fall on the scale of the mean, or of the sample mean, right? Well, so the next step will be to find these numbers here. I have to find the value of t that will give me those things. Okay, so that's what this table is for. The value of t for 0.025 in the tails with 14 degrees of freedom. Down the middle column, across from 14, that t is 2.145. Okay. So let's do our confidence interval. Our x bar, which is our sample mean, is 6, plus and minus 2.145 times the standard error, which is 1.5. Get out my calculator. 2.145 times 1.5 is 3.2175 plus and minus 6. Well, I know what my first one is. I don't need a calculator for that because 6 plus 3 is 9.2175. Now I have to subtract that number from 6. 6 minus 3.2175 is 2.7825. Okay. So now I know that given my sample mean of 6, I'm 95% confident that the true population mean is somewhere between 2.78 and 9.2175. I'm trying to think of something in real life that these numbers can match up to. And the only example I have is slightly obscene, but I'm going with it anyways. All right? No, I'm not. I'm going to chicken out. You all know what it is. So let's say you're manufacturing a device, like a birth control device, and you want to know what sizes to manufacture this birth control device in, because it goes upon an appendage. It's a condom, right? Somebody somehow had to figure this out, right? You're the Trojan company, and you go, we want to make a product. We want to make a product that works, but we only really want to make like 1 or 2 sizes, maybe 3 of the product. It's not like shoes where you have to make wides and mediums and shack size feet. Okay? So you say this is an average, right? All the gentlemen in the office go into the bathroom with a ruler. They come back and they say the average is 6. Well, there's some standard deviation there of 1.5. And you say, all right, how big should I make my device able to work at, size-wise? There you go. You should make something that would do about from 2.78 to 9.2. That's what you should do. Hats. We're talking about hats here. All right. You don't know what the population mean is. You have no clue. You can only guess based upon your sample. Now, what happens as our sample size gets bigger? All right, we would expect that our sample mean would be closer to the population mean. And what will happen with our confidence interval? What will happen to these numbers? Yeah, they get closer together. So instead of having 15 guys go into the bathroom with a ruler, you have 15 million guys go into the bathroom with a ruler. That's a much larger sample. So you should have a smaller confidence interval. Okay? A question like, let's see, I asked you to do number 8, which is based off of a study. So let's do number 6. I don't ask you to do number 6. I'm not asking you to do all of the even ones. The exercises in Chapter 7 included a study designed to measure the number of chocolate chips in a bag. The kids would like this example. A bag of Chips Ahoy cookies. From this example, for the sample of 18 bags of cookies. All right. So the Chips Ahoy folks, trying to figure out if they're putting enough chocolate in the cookies, took 18 chips or 18 trays or whatever of chocolate chip cookies out of circulation. That's 18 that they couldn't sell. Because why? We're going to count the number of chips. The mean and the standard deviation of the chips were found to be, so the number of chips. (1,261 chips. Now, that's only if you eat the whole bag. But the standard deviation of the sample was 114.01, because you got to have that 0.01 there. That's real helpful. Imagine you want to estimate the average number of chocolate chips in the population of Chips Ahoy bags of cookies. Calculate a 95% confidence interval. All right. Thankfully, I'm an expert at this, which means I have 0.0250 in the tails. I'm really good at drawing normal curves. They don't look normal, but that's my bucket on the floor. What's my mean? 1,261. (6A) State the desired level of confidence. Well, what confidence do we want to have? 95%. What's my alpha for 95% confidence? Okay. Calculate the confidence interval and confidence limits. Okay. Well, we're going to do the exact same thing. We're going to do, we have an n of 18. So what's our t-scores for an n of 18 with 0.0250 in the tails? This is a 2.101. So we're going to plus and minus 2.101. Would I subtract 1 from what? Oh yeah, I didn't do that? Nope. Forgot a step. Good call. So it's not that, which is good because I screwed up my equation already. So it's 17 degrees of freedom. It is 2.110. Sorry. Thank you, Jake. Okay. The number of chips was 1,261. That was our average. Plus or minus. Okay. Now they gave us the standard deviation. But the standard deviation is not the standard error. The standard error is the standard deviation divided by the square root of n. All right? They're being tricky, right? Because you all are sort of reading this going, okay, I have this piece of information, this one goes here, this one goes here. But when you read the question, it gives you the standard deviation. It doesn't give you the standard error. So I need to compute the standard error because I'm not using my phone. 0.01, don't forget the 0.01, divided by the square root of 18. According to this, it's 26.872. I'm going to take this answer, I'm going to multiply it by our value of t, 2.110. That answer, I'm going to go up top here, 56.70. Okay. So what are the limits for the confidence interval? Well, 1,261 minus the 56.7 gives me 1,204.3. Let me get this out of the way. And my 1,261 plus the 5670 gives me 1,317.7. So the next time you sit down to eat a bag of Chips Ahoy cookies, I'm 95% confident that you will eat somewhere between 1,204 and 1,317 chocolate chips. Does that kind of scare you? Because like when I make my kids like waffles in the morning, I put like 10 chocolate chips on there. And that seems like a lot. They've got 1,300 chocolate chips in a bag. That seems like a big pile. At least to me. You might be going, well, I want more. Well, that's what you get. Okay. And again, why do we do this? Because if you were to get a large enough sample, right, as our N increases, we want to be more and more sure, this is for quality control purposes, that Chips Ahoy chocolate chip cookies actually contain chocolate chips. Because I've gotten those before. I've gotten a chocolate chip cookie, and you look at the top, and you're like, where are the chocolate chips? You got to look at the bottom, because they're hiding down there. It's usually the last cookie that comes out of the mixing thing. If I do more bags, my confidence interval, these lines are going to stay the same, but this number is going to get closer to the mean. Why? Because as N increases, things like our standard error decreases. Okay. And that's the main reason why. Okay. Questions about confidence intervals? In what tricky ways can you get screwed up on a final exam if you were to be asked a multiple choice question about constructing a confidence interval? This is it right here. All right, understanding what the error is around your mean, that's the thing that I still screw up. Right? Because variance can be difficult. What's the difference between variance, a standard deviation, a standard error? It always has to do with this like n thing, or n versus n minus 1. Right? It's the little details that you go, I don't know which one to use. Well, in the real world, you have the ability to look at things. That's why I give you a equation sheet. Okay. All right, let's do one more. If we look at number 17, it says in the Chips Ahoy cookie example, a 95% confidence interval with the width of approximately 100 was constructed when the sample consisted of 18 bags of cookies. That's about what we got, right? Using the standard deviation of blah as the estimate of the population, blah, 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 blah. Let's not do that one. Let's do part C. How large should n be if we want a confidence interval of 10 chips? So what does that mean? Again, bucket on the floor, draw it out. The average is 1,000, how did I lose this already? 261. I want a confidence interval that's 10 chips wide. What size does my sample have to be in order to get a confidence interval that wide? How would you even start this?
Just plug in 10 to somewhere.
Okay. We're going to reverse engineer it. We know that something has to equal 10. Well, what is that something that has to equal 10? Not quite. The what? We're getting warmer.
Oh, so it's going to be between 1266 and 1257? 50, whatever math is. 1261 plus 5 is 61 minus 5.
Yes. That's what I did to get those numbers.
Oh, sorry up there. Yes.
That's okay. You know how many times I have that feeling a day? Well, let's think about what we just did to find those numbers, right? We used this equation where our confidence interval is our mean plus or minus t times our standard error, which is our standard deviation, divided by the square root of n. The question is asking you to find what? A number of, which of these letters are we looking for? N, right? Yeah? Okay. So we know x. We know we're looking for something that equals, let's do the simple one. All right. 1266 equals 1261 plus t times sigma over the square root of n. Okay. Now here's the deal. This is where it gets difficult. How do we know which t to use? How do we know which t to use? T is, you gotta know n to know t, right? So we quit. Because we're like, screw this. Right? I'm not doing this. This is hard. No, here's what you do. You guess. You guess. And you try something out, and you see if that number works. So let's try out a number. Michigan scored 32 points in its win over Michigan State this weekend. Let's try an n of 32 or n of 33, which gives us a degree of freedom of 32. The t value for a degree of freedom of 32 is 2.037. Okay. Well, our standard deviation was 114.01 because you got to have that 0.01 divided by the square root of n, which was actually 33. So why am I doing this? I just want to see how close I get. 114.01 divided by the square root of 33 equals 19.84. Okay. Times 2.037. 40. Oh, crap. I was hoping that was 5. Right? 5 one way, 5 the other way. So now what do I do? Well, it's got to be bigger than n of 33. So let's look at my chart. At the bottom of the chart, it says infinity, 1.96. Let's see if I can do something with that. All right, let's say we've got a number and it's really big. Well, if I know what 1.96 times this divided by the square root of n should be, right? Shouldn't this equal 5? Since that's the part that's after the plus and the minus, right? I got to see some heads nodding here because this is just math. Do you understand that this is the part of the equation we're focused on, right? We're trying to get this plus or minus thing here to be equal to 5. So let's just break that off. Sorry, I forgot the 0.01. Okay, so if 5 equals 1.96 times something, to get rid of that 1.96, what do I do? Okay, so 5 divided by 1.96 equals 2.55 equals 1114 divided by the square root of n. Now what do I do? Multiply what? Is that what I multiply it by? I am. Or do I divide by 114? No, because I'm dividing by n. This is in the denominator. So this is the same thing as 114.01 times 1 over the square root of n, right? Yeah? So that if I divide this by 114.01, these cancel out, and I get 2.55 divided by 114.01 equals 1 over the square root of n. Right? Okay. And then we finish the math and I'm out of time. If you're looking for the square root of n, you square a number and then that gives you the square root. So I would just multiply that by itself and that would give me the n.